Hello everybody, this is Mr. Steele. I'm here because I really don't know what else to do with my time, and because maybe this is going to be something useful to you, as I said in the message that I sent out. At this point, I'm just kind of picking something to work on and hoping that it might offer you something to work through as well, because really there's no telling what's going to keep happening, and things are getting tighter and kind of stranger and even more surreal every single day. So if you're a person that likes to have something in front of you and likes to work on something and kind of have something to think about to kind of distract yourself from all sorts of things, to help you practice social distancing, I guess, too, maybe this is something that can help. Hopefully it is. In any event, I'm going to work through it, and I'll post these as frequently as I can in hopes that they offer you something to do. So something constructive, something positive as best as possible. So as I start these things up, I'm doing them a little bit differently. Obviously, not having an audience in front of me makes this a little bit different. Specifically, what I've done is I've tried to inject more frequent try-its to the important concepts, the important parts of the lesson. So you'll see a couple try-its in here. I'm not going to go over the answers to those. Those try-its will be available either as a QR code if you're working on the computer at home and you can take a picture of the QR code, or you can access the QR code link using your phone. You can do it that way. Otherwise, I'll include links in the description for this video below in case you want to click on those try-its in the middle and pause the video and make sure you're comfortable with the skills. Now, this first lesson is pretty broad and straightforward. It'll start to get a little bit more specific in the second lesson, and then after that, it's just kind of two small skills for each of those. But again, I'm hoping this is something that can bring you some distraction from all of the strangeness that's kind of overtaking the world right now. So with any event, as I said, I'm picking up the BC curriculum right where we left off with the final 2 units of the course. I'll go as far as I can, or at least until I feel like I've accomplished something and done something productive and useful to you. So with any event, this is the 23rd notes of the BC curriculum, definitely not being delivered in the way you probably expected, and 100% not in the way I expected. So the topic that we'll be discussing in this first one is sequence convergence. Now, we'll talk all about sequences for just a second, all sorts of types, and especially the types you've seen before. And the truth is, this unit isn't all about sequences, it's actually about series. But we start with sequences simply because sequences offer us an opportunity to get some important vocabulary out, as well as to start to, integrate ourselves into the world of sequences and eventually series. Now, something you'll notice in the lesson today, as well as in the lessons over this next couple of lessons. Coming up, I don't have words to describe the situation right now. You'll notice that these topics aren't heavy calculus where if you're rusty on something, it's not going to hurt you too badly here. You'll see when we get to the integral test, it'll be a little bit kind of rusty if you're kind of off. But you'll see all those skills kind of popping back in as we jump in here. So without further ado, as I mentioned, let's start talking about sequences. So to kick things off, I think a really important place to begin is just to remind you what a sequence is. You might be thinking of those glittery, shiny little circles that you put on, some sorts of dresses or costumes of some kind. Those are sequins. These are sequences. So a sequence is best described, at least in my words here. Sometimes I'll go for a formal definition. Sometimes I'll just kind of go off the top of my head here. A sequence is an ordered list of numbers. And when I say ordered, that doesn't necessarily mean that it has to be increasing or decreasing, although very many of them are. And we'll talk about different conditions that allow that to happen. All I specifically mean here is that there's an order to them, meaning that in that list of what we call terms, each individual piece in the list is a term. Each of those terms is in a specific order. So the first one and the second one and the third one are specifically in that place and are generated in that way. So to kick things off, as I have down here, to talk about an ordered list of numbers, I've written out a sequence. I've given you a general rule, sometimes called the formula as well, a sub n, so that is a little subscript n, so a sub n. And it says how we can generate terms in this list, or members of the sequence, no, terms in this sequence, judging based on the number that they are in the actual sequence. So for instance, if we wanted to write out what a sub n looked like, we could start by figuring out what a sub 1 is. A sub 1 would be what we get if we plug in 1. So in this case, that would be 3 times 1 minus 1 all over 2. That's 3 minus 1 over 2, which is all equal to 1. Likewise, we could move forward and we could figure out the second term. Second term would be 3 times 2 minus 1 over 2 to the second. That's going to be 6 minus 1, or 5/4. And then, of course, we could continue forward just fine and continue doing the same kinds of things. So it'd be n equals 3, so 3 times 3 minus 1 over 2 to the third. That's equal to 9 over 8. And what we'd have here is we'd have a list that we could use to generate our sequence, or to describe our sequence. We could say for this guy that the sequence a sub n, notice I'm using the little curly brackets, I don't have a good name for those, but the curly brackets, the sequence would be written as 1, comma 5/4, comma 9/8, and then of course we could keep generating more and more terms if we wanted to. And again, each of these little things here that I'm describing, they're all individually called terms. Specifically though, we talk about the first term as a sub 1 or the third term as a sub 3, so we have names to describe those guys. So from here, again, we have a bunch of different sequences here. You could also, in your sequence, I should note this as well, that if you wanted to write out the full list of every possible term, obviously you don't have time in the world to do that, although for the next few weeks maybe it'll feel like you do. You could then add the term right here, and then add a dot dot dot. By adding the dot 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 at the end, this indicates that it continues onwards so that we could keep adding individual terms. We could keep putting more and more terms in there. But specifically, the reason I bring this up is that term that has n in there, we called it the rule before, but as it's currently written here, sometimes you'll see it called the general term as well. Don't get that confused with the lieutenant or the major term. You know what? I got an idea. Give me one segment. Realizing now that I could have just paused the video, but let me try that one more time really quickly. So yes, we did call this thing the rule earlier, or the formula. Those are accurate names, of course. But another name would be called the general term, not to be confused with the lieutenant or colonel term. This will help me keep my spirits up here as I do this. So anyway, there are the basic lists of sequences. You're seeing all those different things there. Of course, as talking about sequences, like you can tell that these are very related to patterns. It's all about patterns. Like how do you generate these numbers in this sequence? Well, you figure out what the pattern is, or you establish what the rule is, or you're given the general term, any of those things. Now going back a little ways, when you first begin sequence studies oftentimes in school, and I know for many of you, I think for almost all of you, you probably started with like recursive sequences, but we're going to stay away from recursive sequences. We're going to stick with ones that are explicitly defined. I'm not sure. I'd have to look at the difference. I haven't taught Math 1 and Math 2 yet. So anyway, the types of sequences you run into first are the simplest kinds of patterns, patterns that are very clean to work through. One such pattern is an arithmetic sequence, not to be confused with the word arithmetic sequence. That's different. An arithmetic sequence is one whose pattern is addition, meaning that you add the same number, whether it's positive or negative, so technically you add or subtract the same number over and over and over again. Formally speaking, the best definition I can offer for that is that the difference between consecutive terms is constant. So in fact, many people describe an arithmetic sequence as having a constant difference. So what I mean is, let me write out a sequence that is arithmetic. So let's go with, I don't know, 5, 9, 13, 17, 21, dot, dot, dot. So in here, what I mean by saying there's a constant difference between consecutive terms is that you'll notice as you move between terms, I'll use a slightly different purple for this purpose, you're adding the same number every single time. So I'm adding 4 between each consecutive term. What that is this thing is called our constant difference. Now, what is the difference between consecutive terms? Well, that difference is positive 4. It's the same thing as saying we're adding 4 over and over again. As far as generating a list to get your common difference, like there are a couple different ways to get there. For an arithmetic sequence, oftentimes you'll see the formal definition written this way. Like this is a very common way of defining it. This D would be your common difference. N would be the number of the term, and then a sub 1 would of course be the first term. But that's not actually the way that I have learned this rule. Instead, what I typically do is I typically write it in this way. A sub n equals dn plus a sub 0. Now again, I'm describing things in the exact same way, but the reason that this is so useful is that a constant difference in arithmetic sequence, basically the hidden word in all of this is that these are linear. Like there's a linear pattern here. You're constantly adding the same thing over and over again. That's by definition linear. That's the slope basically of a line. You're just adding it multiple times. So in looking down here, the reason this works is that if I'm trying to generate the sequence itself, sure, let's use in fact this one that I just made up here. If I'm trying to talk about that sequence, we could generate a rule or find the general term for this sequence by plugging in the excuse me. Could plug in the first term and then do n minus 1 times that difference, which we said was 4. And that would of course get us our rule. Or you could do what I tend to do, which is to point out that the common difference is like our slope. So we get 4n plus a sub 0, and a sub 0 is the term that would fall before the first term. So following the pattern, if we're adding 4 over and over again, that would make the 0 term equal to 1. So we'd say a sub n equals 4n plus 1. And then this would be our rule or our general term, depending on what we're looking at. And over here, if you're like, well, shoot, why should we get different answers? You don't. It should be more clear here. This becomes 5 plus 4n minus 4, which is, of course, 4n plus 1. So you get the same answer either way. But again, arithmetic is right there. So I'm trying to see, did I miss anything here? No. Common difference. Cool, we did it. Good job, us. So again, you've probably seen that before. Likewise, you've also probably seen geometric sequences before. These are sequences where the pattern is not addition or subtraction, but multiplication or, if you prefer, division. And this is where the ratio between consecutive terms is constant. So once again, let's write out a geometric sequence. We can look at. Let's go with this one. Now, you know what? I've been making everything positive. Let's do it better. Okay, so there are 5 terms from a geometric sequence I just made up. And in this case, just like we did before, we want to talk about this idea of having a constant ratio, or more often it's called a common ratio, but we'll talk about that in a second. So if we look at the pattern to get from here to here, we can figure out what it is that we're doing to get from one term to the next. Well, you can see from 64 to 32, we've obviously got half of what we had before. 32 to 16 is also half. 16 to 8, half. All of them are halves. But because the sign's also alternating and switching back and forth, really think about it as multiplying by negative 1/2. So I need to add a little dot there to indicate that we're multiplying. But basically what we've just shown is that negative 1/2 is what's called the common ratio. Not like it's unspecial or non-unique, just it's called the common ratio because they all have it in common. All consecutive terms have the same ratio between them and the other term. So having said that, like this thing, there are a couple different ways we could write this pattern. Probably the most common way that I see it written all the time is a sub 1 times r to the n minus 1. And in fact, I don't necessarily have a favorite other version of this, but basically this gives us everything. The common ratio is what we call r. So we can talk like a pirate if you want to. R. The common ratio ye be. And then of course a sub 1 is the first term. So in our particular case here, if we wanted to, the sequence that we have written right up there, should we want to write an actual rule or the general term for it, the first term times the common ratio. Notice I'm using parentheses to make sure that we have everything included there. And then to the n minus 1 power. And there is the rule that we'd use to describe that geometric sequence. So let's see, anything else special there? No, not at all. Okay, so you've just seen arithmetic and geometric sequences, 2 very common pattern types. Keep in mind, though, that this isn't like a formal statistic. Like I can't claim to say that I've studied every possible sequence and come to this conclusion, but most sequences are not arithmetic or geometric. They're more likely to be what's called neither. Neither just means they're not just a simple multiplication pattern or a simple addition pattern. They have some combination, or they have some other pattern. Maybe you're natural logging the previous number over and over again. Maybe it is a recursive relationship. There's lots of ways that you could talk about and generate sequences and lists of numbers. We've just seen two very common ones. Now, in the spirit of talking about neithers and sequences that are out there that are more common, like you might be asked at some point to take a sequence and determine whether or not it's arithmetic or geometric, or skipping that completely, you might just be asked to find the nth term or to determine what is a rule that describes the terms of the sequence. How do we govern the change between terms in this case? And I've got one such problem right up here. I have 1/2, 4/5, 16/10. Interesting that's not simplified. 64 over 17, etc. We're supposed to write a formula for the nth term. So typically when I see an expression like this and I start to look at what's there, my first thought, let me make sure I say this correctly. Well, it's pretty simple. What I tend to look at is first I try to figure out if this is geometric or arithmetic, because if it is, I have ways to generate those really fast. In this case, 1/2 plus something to 4/5 plus something to 16/10. It just doesn't look like that's going to work. I've got a feeling it's not going to work that way. I got a feeling. Yeah. I don't think that's going to go anywhere, so I'm not going to go that route. And then second, as I look at the expressions, it doesn't look like we're multiplying the same thing, because like to multiply from 1/2 to 4/5 is definitely not the same thing as 4 over 2, or multiplying by 2. So in fact, it looks to me like this is neither. Like I'm guessing this is a neither. I could be wrong, but I'm looking like this is a neither. So having said that and kind of identified that, of course I could be wrong, but we'll see what happens. Instead, what I'm going to recommend we do is that we focus on two separate patterns. Let's look at and isolate the pattern that's in the numerator. We'll work with that a little bit, see what happens. And then second, let's work on and isolate the denominator pattern and see if maybe we can develop a rule or a general term for this guy separately by looking at each case individually. So in our numerator, the sequence I see is 1, 4, 16, 64. And having said that, that's a huge accomplishment because now I can already see what the pattern is. Can you see what the pattern is? It doesn't work. No. Yeah, it doesn't really. That doesn't really help in this situation, so never mind. I'll just assume that you said, yes, I can see the pattern does appear to be geometric. This looks geometric. If you're wondering why it is, it's because I can see that there's a common ratio. I can see that to go from 1 to 4, you multiply by 4. From 4 to 16, you multiply by 4. From 16 to 64, you multiply by 4. That's telling me that my numerator is going to be governed by a geometric pattern. In fact, I'm thinking that's going to be 1 times 4 to the n minus 1. Let me do a quick little check. If I plug in n equals 1 here, and again, something I haven't maybe established as much is that like each term corresponds to one of the counting numbers. Should have said that earlier, I apologize. If we do it this way, n equals 1, we'll get 1 times 4 to the 1 minus 1, which is 1. Yes, that works. So, but we don't need the 1 in front, so we can just write this as 4 to the n minus 1. And again, that's not our answer, that's just our numerator. We know that the numerator of these terms is looking like powers of 4. Likewise, we can look at the denominator. Since the denominator wasn't, since that third term wasn't simplified, I'm thinking it's a good sign to look at it this way. 2, 5, 10, 17, ... Now, if you look at this, you might get excited and go, oh, cool, we're adding 3 every single time. But don't get overly excited, because then we're adding 5, and then just for kicks, we're adding 7. So unfortunately, this tells us, because they're not all the same, that means there's not a common difference, which means that in fact, in this case, this is not going to be arithmetic, nor is it going to be geometric, but beside the point. Instead, what I want to point out is that there's actually something else that happens here. Because our first difference was not arithmetic, or was not constant, that means it's not arithmetic. It means it's not going to match a linear pattern. But since the common differences were all, in fact, arithmetic, that produces what's called a second difference of positive 2. So since the second difference is positive, this is just kind of a nice thing. This tells us that we actually have a quadratic relationship. Now there are a couple different ways you could use this information to generate your quadratic relationship. Something you may find out later on in the course, or you might know already from other problem solving work that you've done, is that to figure out the coefficient of that quadratic thing, something over something n squared, you take the common difference and put it over 2. So in this case, this is going to be an n squared pattern. It'll be n squared plus something. And at this point, though, I just want to point out that I think we can actually figure this out without much extra work. 2 is 1 plus 1. 5 is 4 plus 1. 10 is 9 plus 1. I probably should have seen this at the beginning. I did write the question after all. And 17 is 16 plus 1. So what that tells me is that I have a feeling the pattern in the denominator is just n squared plus 1. And in fact, based on for all intents and purposes, it looks like it is indeed n squared plus 1. So given all of that, that allows us to generate everything together. We can write out our formula. In this case, the general term or the rule or the formula for this entire thing appears to be 4 to the n minus 1 over n squared plus 1. So there is our rule that we'd use to generate terms of this particular sequence. And now this problem doesn't ask us to do it, but if we wanted to, we could now go through and find something like, say, a sub 5. We could say really easily that a sub 5, the next term, or heck, let's just go even higher. A sub 6, that's going to be equal to 4 to the 5th over 37. Now I don't know what 4 to the 5th is off the top of my head, but same as 2 to the 10th. But the point is we could generate those terms much more readily because we have the general term, or we have the rule or the formula to generate terms of the sequence. So technically, by the way, we haven't actually done any calculus yet. We've just been reviewing sequences, but at the same time, it's good to get you kind of back in the flow of things this way. And having said that, I've created a short try it for you if you'd like to kind of review some sequence stuff, just to kind of get your mind around what's there. So in this case, you've got a couple sequences to identify as arithmetic or geometric. Both 1 and 2 kind of use the same list of 5 sequences. And then number 3 asks you to find a term of a sequence. And in this case, there's no real punches pulled. Basically, things have been simplified possibly, so maybe that's something to look at as you work your way through. Having said that, again, I'm not going to dwell on these. I'm not going to give you the answers. You can go to the link in the video description, or you can use the QR code and go work through this. If you want to, if you feel like you're good, go ahead and proceed forward with the lesson, just like I'm going to. Okay, now that we've looked back at sequences through the ages, what we want to move on to is the stuff that actually relates to calculus. And that's going to begin with some terminology that we're going to use throughout the rest of this course, wherever that course takes place. So that terminology is convergent or divergent, as well as the words converges and diverges. So we'll start with the definition here, but this is going to be something that's kind of huge. And if you're thinking about in calculus where we've heard these terms before, we did use convergent and divergent to describe improper integrals. So they aren't completely new terms. So what it says about a sequence. So first it says let L be a real number and let A sub n be a sequence. So we're talking about some sequence A sub n, and we're talking about some real number L. It says in this definition, if the limit as n goes to infinity of a sub n, our sequence, is equal to that real number L, then we say a sub n converges. And you know what, in fact, I'm going to add a little bit something to it. We not only say that the sequence converges, but we say specifically that the sequence converges to L. So should we include that as well? So basically, if the limit as n goes to infinity of a sequence is equal to a real number, then we say the sequence converges. Otherwise, we say that the sequence diverges. So now what we're talking about here can be a little strange to look at for the first time. It can be kind of weird the first times you're kind of thinking about it, simply because what it's describing isn't necessarily something we've ever had to think about before. We tend to think about sequences as ways to talk about like the 11th number or the 15th number, or just kind of a general description of what the terms would be in the sequence in case we wanted to generate those. But in this case, what we're interested in is what do terms look more and more like, or what value do they get closer and closer to as we go further on in the list of terms of this sequence. So I'm trying to think if there's a way that I could do this. I don't think there's an easy way for me to generate it, so I'll hold off until the next page. But keep in mind as we look at this, we're really just talking about terms. Like where are the terms going if we go on forever in this sequence and just keep generating more and more terms? Now in here, if we're talking about a real number L, make sure that you're careful because that means that there are some other conclusions. Like we know the one conclusion that's required if you want the limit to converge. It has to converge to a real number. If, on the other hand, your sequence diverges, then there are lots of possibilities here because there are lots of ways you can be not a real number. So, of course, one way would be if your limit as n goes to infinity of a sub n is equal to either plus or minus infinity. If you equal plus or minus infinity, that means that your terms are what's called growing without bound. They just keep getting bigger and bigger in magnitude. And unfortunately, that doesn't allow us to say that it's converging to a real number. Therefore, it diverges. Likewise, and I can't necessarily come up with a good example, or I can't come up with a meaningful example for this, but for the moment, if the limit as n goes to infinity is equal to some complex number, so in other words, if the value of your limit has an imaginary component, that's also going to be something that we'll say diverges. Like I'm thinking of something with like the square root of negative something, which, yeah, it's clearly not going anywhere. Likewise, and this one I can actually come up with some examples for, and you probably can too. If your sequence is something like the sine of n, in this case, this limit does not exist. So does not exist is another possibility for a sequence that diverges. We just don't have a way to get there because, of course, sine oscillates between two values. And then likewise, if we're talking about other things that are not real, we could say, of course, the limit of some sequence is equal to could also say it's equal to a unicorn. If the limit of the sequence is equal to unicorn, unicorns aren't real, so the crowd agrees that was funny, so I'll pause for your laughter. But yeah, the idea is we have to have a real number if we want a sequence to converge. And again, we're curious what's happening as we go further and further along to see where this thing's actually going. So from here, a good place to begin is just kind of look at a couple examples and show you what it's like to check if a sequence converges. In this case, we're leaving no ambiguity. We're saying, we're demanding, we're telling you, instructing you, I'm telling you, show that this sequence converges. So that's pretty simple. According to the definition we saw, we'll show that a sequence converges if the limit as n goes to infinity of its terms is equal to some real number L. That's all we're looking for. So in this case, what that means is we want to look at the limit as n goes to infinity of 2n squared minus 5 divided by the square root of n to the fourth plus n squared plus 2. Now there's lots of different ways to attack this particular limit, but because we're going towards since we're going towards positive infinity, it's nice to point out that we can evaluate this limit pretty simply. We can just look at this, and we could, of course, well, there are a couple different ways. One way we could do this is we could go through and we can multiply up and down by things, but instead what I'm going to do is I'm going to use some controlling term analysis here. It's not the most formal way to do things, but because we're going to infinity, this will work really nicely. So keep in mind, as we get larger and larger values of n, aka we're moving further and further deeper and deeper into the sequence, further along, we're plugging in larger values of n for later terms of the sequence. There's what I was trying to say. Then there's only certain terms that really matter, because that growth of that n is more powerful. So in particular, in the numerator, 2n squared is going to control all the growth, because 5 just isn't growing fast enough. It's just a horizontal line, so we're just going to ignore it. Likewise, in the denominator, be the same thing as the square root of n to the fourth. Now, in looking at this, because we're going towards positive infinity, sign isn't an issue. SIGN, by the way. Instead, that means it's the same thing as 2n squared over n squared. And that, of course, is equal to 2. Now, 2 is a member of the reals. 2 is a real number. You count 1, 2, 3, 4, unicorn, 6, 7. Yeah, it seems like that's there. So it's definitely a part of the reals values, which means, for our purposes, we have all that we need. So all we have to ask ourselves is 2 real, and it does. In this case, we can say that the sequence a sub n converges. And of course, we can go that one step further as well. We can say not only does a sub n converge, it converges to 2. So that means if we look at later and later terms of the sequence, they're going to get closer and closer to 2. It'll just look more and more like 2 the further along that we go. So kind of an interesting thing to think about. Do I have a calculator that could generate this? I don't have a calculator app on the here anymore, but I'd love to be able to show you that this actually is true. But for the moment, we'll be okay. Now, you know, let's do it. Let's go look at Desmos really quickly, just to kind of illustrate the point. Yeah, here we go. We'll go a of n equals, let's go with, we had 2n square root n to the 4th plus n squared. Should have thought about this before, but again, this is a strange week. Forgive me for not thinking of such a thing. Plus 2. Okay. Okay, so we're calling this. Okay, add a value of k. Okay, so what you've just seen here, this is, I'm just going to put a lot of values in here. So, kind of tough to see. There we go. Now you can see for sure. So I've put in our sequence itself. I've written it a little differently. I've treated it as a function. And then I've told it to generate values of k and then plug them into the function. And we want to see what these values of the terms, basically, of this thing are going to get closer and closer to. I'll even make the step 1 so it's truly a discrete valued function like sequences are. Ha! Wow, it moved really fast. Maybe that was too fast. Maybe I made too large a thing. Okay, so here we go. We'll just go with 100 terms. So watch the values there. I'm going towards 100. Notice that it sure looks like we're getting pretty close to 2. Look at that. We're down to 2.0007. In fact, I bet if I go to 1,000, let's see if maybe this is too much for Desmos. Yeah, look at that. It is definitely getting closer and closer to 2. So that confirms what we saw. What we saw was that the further we go along, so like right now, by the way, we're at like term 890. We're at a sub 890 of this sequence. The value of the term is 2.00000050. So basically this is confirming that in fact the limit of the sequence is converging to 2. Graphically speaking, by the way, we can also kind of see that as well. Notice that this does in fact seem to have a horizontal asymptote at around 2. It just looks like it's getting closer and closer to 2, just like our little values are showing us there. Okay, having seen that, of course, sometimes it's not going to be quite so easy to check if a sequence converges or diverges. So this is one such situation where it'll be a little bit trickier. So it asks us to determine whether the sequence, 2 to the n plus 1 over n to the third, converges or diverges. So in this case, one thing we could do is we could just go over Desmos and play with it and just kind of look and see what happens. But of course, we won't necessarily have a graphing calculator for this question. In fact, this exam for this kind of unit is typically non-calculator anyway. So in here, oops, that's not the purple that I like. Let's do this right. Do the limit as n goes to infinity of 2 to the n plus 1 over n to the third. Okay, now, looking at this realistically, the first thing you might notice is that if you try to plug in infinity on top, you get 2 to the infinity plus 1. And that is really big. That's infinity. Likewise, the denominator goes to infinity cubed, which is also infinity. And because we have a limit with an indeterminate form of infinity over infinity, that means that we can use L'Hopital's rule. So I'm going to use L'Hopital's rule. Now, L'Hopital's rule is easy to use in the denominator. We take the derivative of the denominator. That's 3n squared. The numerator, though, sometimes messes with people. So it's worth taking a moment to remind you of how to differentiate a function like 2 to the n. So let's take the derivative with respect to x of 2 to the x. So if you want to do that, like there are a couple different ways to get there. The first way that you might do is you might rewrite the function as y equals 2 to the x, natural log both sides, because natural logging both sides allows you to bring down the power. So that would be ln of 2 to the x, but I've brought it down, and I've got it written as x times the ln of 2. Now ln of 2 is just a constant, so when we finally differentiate this with respect to x, we're going to get implicit differentiation on the left side. That'll be 1 over y times y prime. On the right side, we'll have a number times x, which is linear, and the derivative is just the slope. Having said that, we can multiply y on both sides. We'll get ln of 2 times y, which is the same thing as ln of 2 times 2 to the x. So there is the derivative of 2 to the x. So it's a rule that's easy to remember. It works for e as well, by the way. That'd be ln of e equals times e to the x. So however it is we get there, we now have the numerator is the ln of 2 times 2 to the n, and then plus 0 because that's gone. Good news is L'Hopital's rule is applied. The bad news is our denominator goes to infinity, and our numerator goes to infinity. So I hope you like L'Hopital, because we're going to do it again. Just thinking, I wonder if the YouTube thing will like flag my video if I start humming 80s songs. Sorry. So the denominator, 3n squared, if we use L'Hopital again, that'll give us just 6n. In our numerator, we've now got a constant or a scalar of ln of 2 times 2 to the n. Well, if we take the derivative, the ln of 2 will stick around because it's a scalar, and the derivative of 2 to the n will once again be ln of 2 times 2 to the n. So that means our numerator will now have 2 ln of 2's being multiplied, which I'll write as ln of 2 squared. And then that's all multiplied times 2 to the n, which, bad news, is going to still give us an indeterminate form of infinity over infinity. Now at this point you could probably, well, we're one step away from finishing this off. Let's not obscure that fact. We're almost there. But what I wanted to say was that if this power was larger than 3, this might not be a practical strategy. You might not be able to do it or reasonably able to do this 1,000 times. So it helps to know what's called relative rates of growth or relative magnitudes of functions to see that an exponential function grows a lot faster than the polynomial does in the denominator. But again, for small powers or small values, we can do this pretty easily as well. And in fact, let's not wait or prolong the inevitable. We know what's going on here. We'll get ln of 2 to the third power now times 2 to the n in the numerator. And in our denominator, we just get 6. So at this point, if we go to evaluate this, we'll have infinity divided by 6, which is infinity. Now, yay, we're done L'Hopitaling. That was a lot of L'Hopital. That was L'Hopital much. It's uncomfortable doing that in a very empty house. It actually kind of creeps me out, but you know, hey, whatever. Can't go anywhere else. So in any event, what we just found was that, hey, we now know what the limit of that thing is equal to. This tells us that the limit as n goes to infinity of a sub n is equal to infinity. Infinity is not real. Well, I mean, it's not a real number. Let's put it that way. It's not a member of reals. So therefore what this means is that a sub n equals that thing, which had that exponential numerator over that cubic denominator. It means that sequence diverges. So in this case, what that's telling us is that the further and further we go along the sequence, the later and later the terms we examine, their values are going to keep ballooning and keep getting bigger. So we're not going to be approaching a number like we did on the last one, like we were getting closer and closer to 2. This time we're going to get just larger uniformly. We're going towards infinity itself. That was a terrible circle. That was also. We're going towards infinity. So of course, let's see. Again, like I can take advantage of this stuff because I have nothing else that I can do right now. Let's look and see what happens with this thing. So I'm going to write this one as b sub n, and I'm going to write it exactly as it was. So we had n to the third in the denominator. We had 2 to the n plus 1 in the numerator. And then let's look at b sub k. So I'm going to move k down so we can examine it the same way we did the other one. Oops, just a second. So let's watch values right here. It says b sub k of 0. Okay, so as we start, holy moly, did you see that? That went really fast. Like as we plug in values, oh, it's jumping by 10. Let's try to 100. So it starts as 3, that's benign. And yeah, it's getting bigger. Oh, yep, look at that. We're up into the 800,000 range. We're only on the 36th term, 37. Oh, look at that. It ran out of decimal places. It didn't want to keep showing it. Yeah, can you agree that it looks like the terms of the sequence are growing bigger and bigger? Because I'm pretty comfortable with it myself. That the 100th term is 25 digits long. Not ideal. Somewhere in that ballpark. So again, let's also look at it this way. Like, we're talking about sequences. So looking at the terms of the sequence would be this purple thing. And look at that. Unlike the red one, which is flattening as we go forward, the purple one just keeps getting bigger and bigger. And yeah, it's a weird looking shape. But yeah, that's pretty much textbook definition of going to infinity. So in fact, what we've just seen is what a divergent sequence actually behaves like. And in fact, we proved that it was divergent by looking at its limit as n goes to infinity. Having said that, this is the last super important, crucial part of the lesson. So I want to give you an opportunity, if you'd like to practice this and work with this vocabulary a little bit, as well as just kind of exercise some of those limits at infinity skills that you might not be using. So as with the last one, if you're on a computer, you can use your phone. You can just quickly, let's see, will it work for me? Boom. What do we got? Ha. Yep, it worked great. Good to see that that works. So if you're at a computer, you can use your phone to get there. If you're doing this on your phone, if you're looking at the lesson on the phone, you can just look at the link in the description of the video that will take you to the second try it. But again, give you an opportunity to do a little bit of thinking and problem solving and practicing with this new terminology and the actual first part of the calculus part of this new unit. Okay, having looked at that try it, hopefully you have. Hopefully you've gotten some good practice out of it and feel really confident with the words. We're going to move on to the last portion of this lesson, which concerns two other properties of sequences. Now, I will admit going into this that this is not the portion of the lesson that's going to be the most crucial. You're going to use it every single day. But they're important concepts nonetheless, and they're the kind of thing that I just kind of want to talk about and let you get in your ear and to think about, to kind of provide context for the rest of the work we're going to do. As well as to lay foundation for future mathematical work. Like, this is not the exactly how I'm going to assess it. I'll ask you some questions about these concepts, but they're not quite the same level of importance as being able to tell if a sequence is converging or diverging. So in here, the first thing we'll start off with is the concept of monotonicity. And I believe I'm saying that correctly. Basically, we want to be able to decide if a sequence is what's called monotonic or not. So it says in here in our definition that a sequence is monotonic if the terms of that sequence are either non-increasing or non-decreasing. So now this is specifically non-increasing or non-decreasing. It's not saying it has to be strictly increasing or strictly decreasing. So you're allowed to have kind of flat growth for a while. You can have some places where the sequence is constant or flat for a little while. But specifically, there's never allowed to be like a dip. You can never have a moment where suddenly your sequence drops down. So when we're talking about monotonic, and we should probably talk about this. If you're graphing sequences, I don't know if this has ever been brought to your attention, but sequences are defined over the counting numbers, also known as the whole numbers. So basically, even when we're looking at an arithmetic sequence, you might have pictured something like that. But in fact, for sequences, it looks more like this. This would be the graph of a sequence. So the reason I bring this up is since this is a sequence, this would be values of n, or the number of the term, versus values of those particular terms. What I've just drawn is what I would call a non-decreasing sequence. Some might just call that an increasing sequence, and yeah, it is strictly increasing according to what I'm seeing. But what you can kind of see as you look at it is that there's never a place where it starts to dip down. If I had dropped one of these points and gone like this, well then unfortunately this sequence is not uniformly non-decreasing. There's an interval on which this decreases, in which case we would then say that this would be non-monotonic. So specifically because it's just going up the whole time, we have something that's non-decreasing. This sequence is in fact what we would call monotonic. And again, I'm using a graphical depiction just for simplicity. We'll look at a real one in just a second. On the other hand, you could also have a sequence that looks a little bit different. It doesn't have to be quite that uniform. You could have something like this. So, and again, what this one looks like, if I just kind of trace it through so you can kind of see it for a second. Oops, that was a bad draw. It looks like it gets flat for a little while and then continues downward. So right there it's constant, but that's okay. This is just what I would say is non-increasing. And this would be definitely monotonic as well, at least assuming that I've drawn it accurately. If you're looking for something that's non-monotonic, which, to be fair, is not really a fun thing to say, non-monotonic, or the non-monotonicity, I sound quite intelligent when I speak that way. If you're looking for something non-monotonic, well, that's pretty simple. It can be as simple as a quadratic relationship like this. Oh, those look like dashes, I'm sorry. This would be something that's non-monotonic. And specifically the reason for that is that it's increasing for some portion and it's decreasing for the other. So it doesn't meet either of those definitions. So unfortunately both of those are out, so that makes a non-monotonic sequence. Now as it shows in here, we have kind of this approximation. This is also a definition. These are going to be the tools that we use if we want to algebraically show that something is monotonic. We'll have to check whether or not that holds for all values of n for the particular sequence. In other situations, as you'll see in just a second, you can actually make determinations about the monotonicity of a function simply by looking at the first few terms and seeing if it matches, seeing if it happens to decrease or increase in a way that doesn't describe the rest of the growth of the sequence. So let's look at that. So here is one such question we could ask. Is a sub n equaling n squared over 2 to the n monotonic? And again, if you were going to try to prove this algebraically, what you would have to do is you'd have to look at a sub n plus 1 and check whether or not it's less than or equal to a sub n uniformly. Or possibly the reverse. It could also be the reverse. For us, though, since this is something fairly small, before we start looking algebraically, let's just check a couple terms just to make sure. So in fact, there's not really a name for this strategy. It's just simply, I was going to say intuition, but it's not really that. It's just kind of that algebra stuff looks like it might be hard. Let's just see if this looks even like it might potentially be monotonic. So what that means is I want to generate terms of this sequence. So to do that, let's grab a color here. Enjoying adding some color here because it is fairly gray outside. Oh boy, it's been gray. What a great way. Oh, what a gray way to usher in this awkward time. That one didn't make me laugh. So anyway, we'll write out a few terms of this sequence and see what happens. So basically what we're going to do is we're going to write out a sub 1, a sub 2, a sub 3, a sub 4, and at that point we'll see if there's any violation of the definition of monotonicity, and if we might need to do algebra. So in this case, I'm going to find a sub 1 first. That's going to be 1 squared over 2 to the 1. That'll be 2 squared over 2 to the 2. It's going to be 3 squared over 2 to the 3rd. 4 squared over 2 to the 4th. That's terrible looking 2. And terrible 2s. It's a real thing. Okay, so in looking at this sequence, what do our terms look like? We have what appears to be 1/2. So after one term, is it monotonic? Heck yes, because there's no way to be non-monotonic with one term. For the second one, we have 1. Okay, so now, having said that, right at this moment, we've established something. In order for this sequence to be monotonic, that means since 1/2 went up to 1, that means we've established this is a non-decreasing sequence. So if we want this to work, we need the third term to also be larger than 1. So let's see. 3 squared is 9 over 2 to the 3rd, which is 8. 9/8 is greater than 1. It looks like we're moving towards monotonicity. Let's check one more just to be safe. Let's just make sure. We have 4 to the 2nd, which is 16, over 2 to the 4th, which is 16, which is 1. And, aha! Imposteur! Is that French for imposter, maybe? I don't know. What we've just shown is we've just shown a violation. Basically, from 1/2 to 1, we were increasing. From 1 to 9/8, we were increasing. That's an R. Increasing. From 9/8 to 1, we are decreasing. I think it's j'accuse. There's the word I was looking for. I just don't speak French, so it wasn't there. Basically, what we just saw was we established a pattern of non-decreasing, and then suddenly it decreased. So unfortunately, what that tells us is that a sub n, n squared over 2 to the n, is non-monotonic. And I always have to check my spelling here. Non-monotonic, yes. So there is our first piece. So in this case, we didn't actually have to do anything particularly fancy. All we really needed was to check the first couple terms, and it turned out since the sequence was non-monotonic, it didn't even hide. It wasn't even disguised for a long time. It was just kind of waiting for us to see. So we didn't need to do any of that algebraic work that we'll have to in just a second. So don't be afraid when you're looking at something, checking to see if something's monotonic, don't be afraid to just look at the first couple terms, because that might be enough for you to actually get there. In fact, I'd highly recommend it, because odds are if I'm asking you to do it this way, you're probably going to have a non-monotonic sequence. But you didn't hear that from me, except in the moment talking, so yeah, whatever. Now on the flip side, that's not always going to be the case. So in this case, we're looking at a situation. We want to determine if this sequence, 2n over n plus 1, is going to be a monotonic sequence. So while I said that you could check the first couple terms, but sometimes you won't, in this case I do think it's important for us to check the first few terms just so we can determine, there's a pun in there, just so we can determine which of these we want to look at. Is it going to be a less than or equal to situation? Are the terms going to be getting bigger, or are the terms going to be getting smaller? So in this case, let's actually kick things off by looking at the first few terms. So let's look at what the first few terms are to look and see what we're trying to prove. So we want to see if it's monotonic. Let's see if that's possible. So if we plug in 1, I get 2 over 1 plus 1, which is 2 over 2, which is 1. If I plug in 2, I get 4 over 3. So at this point we have, well, let's go a couple more terms. Let's just find out. The third one would be 6 over 4. And the fourth one would be 8 over 5. So it looks to me like the terms are increasing. Now again, it could just be a mirage. It could be that only the first 48 terms are increasing and then after that it decreases. But for the moment, if we're going to show this as monotonic, if that's even a possibility, we're going to want to show that the further along terms are larger than their predecessors. So what that means is we're going to try to show that a sub n plus 1 is greater than or equal to a sub n. So that's our goal. We want to show that this is true. We want to show that it's true for all n greater than or equal to 1, which would be the ones in our sequence. So let's do it. Let's give it a shot. Let's see what happens. So what does it look like when you're trying to do this algebraically, basically? Well, first what we want to do is we need to figure out what a sub n plus 1 is actually equal to. So in fact, let me do this once. Let's change the color of it. A sub n plus 1 is going to be whatever we get if we plug in n plus 1 to n for n. So in this case, a sub n plus 1 would be 2 times n plus 1 over, geez, that's a terrible fraction bar. I am ashamed. There we go. Over n plus 1 plus 1. So that's a sub n plus 1. And then, of course, what we want to show is that that's greater than or equal to 2n over n plus 1. Having said that, we probably want to clean this up a little bit. It'll help us a little bit to start moving through this. It looks like on the left side, we're going to get 2n plus 2 divided by n plus 2. And then on the right side, we're going to be comparing that to 2n over n plus 1. We want to show this is always true. We want to see that it's always true. So at this point, a couple things to note. First of all, I'm going to say this is for n greater than or equal to 1. So I do want to establish that so that we're only using values that we'd use when generating terms of a sequence. But from here, basically, it's just kind of an algebra game. So how am I going to attack? Well, what I'm going to do is first I'm going to copy this so I can do it again. Let's go one more time right here. So I'm going to take this expression, I'm going to multiply both sides. I'm going to basically clear the denominator. Just think that's probably a good idea. So I'm going to multiply the left side up and down by n plus 1. You know what, I got to do this right. I feel wrong not doing it that way. So I'm going to multiply both sides by n plus 1 times n plus 2. And if you're someone looking at this going like, why are you bothering with this? Why are you trying to do all of this? Or better yet, why are you allowed to do this without affecting the sign? Well, n is always going to be positive, greater than or equal to 1, so it's always going to be positive, so we're allowed to multiply both sides without changing the inequality. And 2, I'm basically just fraction busting. I just want this thing to be a little bit clearer for us to look at so we can compare the two sides. So on the left side, we had 2n plus 2. We're now going to multiply n plus 1 times the artist formerly known, or times 2n plus 2. And then we're going to try to show that that's greater than or equal to, on the other side, it looks like 2n times, where'd it go? There it is, pink, times n plus 2. So this is now our relationship we're trying to work our way through. So having done that, let's try to simplify this and clean it up a little bit. I'm going to do a little bit of multiplying. On the left side, we'll get 2n squared plus 2n plus 2n plus 2. It's a lot of 2's. Is it too much 2? I don't know. And then on the right side, we're going to have 2n squared plus 4n. So cleaning things up a little bit further, I'll see 2n squared plus 4n plus 2 is greater than or equal to 2n squared plus 4n. Now, hopefully you're seeing the same thing I am. Like, this is kind of nice. If I subtract 2n squared from both sides, and if I take things further and I subtract 4n from both sides, that's going to give me the new inequality. We've got a lot of things zeroing out, and all we're left with is 2 is greater than or equal to 0. Now ask yourself the question, is 2 greater than or equal to 0? Yeah, it is. Definitely greater than or equal to 0. This is always true. And what that means is that our original relationship, a sub n plus 1 is greater than or equal to a sub n, is always true also. So what that means is we've actually just proven that this statement holds. It means that the next term, or the n plus 1 term, is always greater than the nth term. That means the terms are, in fact, are non-decreasing. I'd rather just say increasing. In fact, I'm going to. You know what? No one's going to stop me. The terms are increasing, and since that's true, we can therefore conclude that by definition, a sub n equals 2n over n plus 1 is monotonic. So we've actually just proven it. So probably what you're coming to the conclusion of, if you've even stuck through this portion of the video, is you're like, yeah, this isn't fun. This is just like annoying algebra. And you know what? You got it. That's right, it is. But again, like I said, this isn't a huge part of this unit. I just want to make sure that I cover everything that's included in this unit in case you decide to skip through this course or you run into it again in the future. I'd rather invest that time now, especially because, well, I got nowhere else to be. So there it is. We've just shown as monotonic. What that required, like if you're looking for a recap, what we did was we generated a few terms. I'll do this with a little star to kind of indicate what I'm describing. We looked at a few terms to develop whether or not an increasing or decreasing pattern seemed to be there. After that, we set up the algebraic system, and we started to compare all of the pieces together. We did a bunch of algebra until we ended up at an inequality that was either always true or never true, or sometimes true even. And then finally, we were able to draw our conclusion and state that the sequence was monotonic. So there it is. That is monotonicity in both a visual way, a quick checking kind of cheating the system way, and then the more formal algebraic manner. Having said that, monotonic is great, but despite the root or the prefix mono suggesting 1, there's actually a second property that's valuable, and in this case, a property that's super valuable about showing whether or not a sequence is going to converge or not. Having talked about convergent, the other property that we're going to address is called boundedness, whether or not you can describe numeric values that are always larger or always smaller than the actual sequence. So it says in here that a sequence is bounded if there exist m and n, real numbers m and n, such that a sub n is always greater than or equal to m and less than or equal to n for all n. Now this is even less of an essential concept, although it's one I think that's easier to understand than monotonicity, or definitely easier to prove than monotonicity, but we're not going to go into a ton of depth about boundedness. Instead, I just want to kind of talk about a couple different examples really quickly to give you some context, and then we'll show you why we're even talking about this concept that's not quite as essential as everything else. So quickly, I'm going to draw in a couple different pieces here. Actually, no, I'll go right there. Nope, that just looks not quite happy enough for me. Okay, so what I've got here, I'm going to draw two different sequences. So the first one I'm going to draw is this, and the second one I'm going to draw is this. So those are two sequences. Now the first question I'd ask you to see if you understand kind of the general principle of boundedness is to ask you which of these two is bounded. And your answer, were I able to hear you, would surely be the first one. This first one, oh, that's weird. This graph on the left, the sequence graph on the left, is bounded. And the reason is we can actually construct and find values that bound it. that are always larger and always smaller respectively. So for instance, it looks like I've drawn a sine curve, by the way. We could draw a line right under here and say that that's going to be a lower bound, and this one up here will be an upper bound. So in this case, we could say that this value would be our value of m. I might say it's -4. And our upper bound would be n equals, 42. So what we're describing are two different types of bounds. We have an upper bound, and I just chose to make that upper bound 42. And then we have a lower bound, which I decided to call -4. Now, having said that, you might think to yourself that if this sequence was in fact something like the sine of n, maybe those aren't the right choices. Like, those aren't the bounds, because couldn't you choose -1 and 1? And the answer is yes, absolutely. You could talk about -1 and 1 being the lower and upper bounds. We could choose those. In fact, those guys are special. Not that you need to know this terminology at all. This is definitely not a part of AP calculus or even like lower division calculus. But if you want the least upper bound, I'm going to abbreviate that as least UB. That thing is called the, let's make sure I call this correct, the lim supremum, which I'm realizing now, because American Horror Story didn't exist when I was in college, the lim supremum, or the lim sup, sounds kind of hungry, lim supremum is actually the least upper bound. So in this case, for sine of n, the least upper bound would be 1. It's the smallest thing that's always greater than or equal to the function. Likewise, you could talk about the greatest lower bound. Oops, grease. The greatest lower bound. And that greatest lower bound also has a name. It's called the lim infinum. And that would be, in this case, -1. Having said that, boundedness doesn't require that we find the lim supremum or the lim infinum, also known as the least upper bound or the greatest lower bound. All it requires that we find is an upper bound and a lower bound. We have to find both of them. Now, having said that, look over at the difference on the right side. If we look on the right side, we can very quickly establish the fact that there is a lower bound. Like, the lower bound here, it looks to me like I could choose a lower bound that's any negative number. So I might say that the lower bound for this sequence on the right is, -1. Having said that, though, there is no upper bound. It looks to me like this sequence is just growing without bound. In fact, I might even want to say that this is a convergent, or excuse me, a divergent sequence. So in fact, this would be a sequence that we'd call unbounded. And in fact, even though it's bounded in one side, it has no upper bound, so it's an unbounded sequence. So now, the interesting thing here is that there's this interplay between boundedness and monotonicity, these two concepts. One talking about the fact that you got values that kind of lock in the values of the terms of the sequence, and the other one is talking about its uniform growth, either growth or decay. It's non-increasingness or non-decreasingness. So in fact, the reason we bring these up is that there's a theorem that actually guarantees that a sequence converges. Now, as I've said multiple times, this isn't the crux of the lesson, but I want to deliver all of it to you anyway. So in this case, the theorem that's in question, one that's probably at best, probably like a true or false kind of statement in the future if you're looking at future exams for this course, the theorem says if a sub n is bounded and monotonic, then a sub n converges. So it's basically saying if you have those two properties that we just talked about, so if your sequence is bounded, meaning that you can find both an upper and a lower bound, so your sequence has an upper and a lower bound, and your sequence is either non-increasing or non-decreasing, then the sequence has to converge. Now, the reason why this is best described by just kind of comparing what we've seen so far. So, heck, we could even look at our two examples from here. What we've got, let me see if this can work. I should have thought about this before, but that's okay. Got so much more space to work with. I'm trying to use space a lot better here since you might be looking at a phone. So looking at these two, we have two options. We have on the left side a bounded sequence, but it's a non-monotonic sequence as well. The reason is, of course, it starts increasing, then it's decreasing, then it's increasing again. It's unfortunately only one of those properties. So while you can construct an upper and a lower bound all day, the sequence just isn't uniformly growing. On the right side, we have a sequence that's monotonic, but it's unbounded. So neither of these two allows us to talk about a convergent sequence. I mean, in fact, look at that. On the left one, our sequence is oscillating, so it's not going to have a determined limit as we go to infinity. On the right side, that limit as we go to infinity of the terms of the sequence is infinity, so it's growing without bound. What happens here is we're talking about a different situation if you have both of those properties. And again, this is non-rigorous. This is not a rigorous proof of this property, but hopefully it's a nice intuitive one for you to hold on to. So if we have a sequence that's bounded, then that means that all the terms are between two lines, two horizontal lines. Their values are always going to be capped. So for instance, I could say those are our lower bounds. I think we went with n on top, yeah. There's an n and there's an m. Likewise, we say that the sequence has to be non-increasing or non-decreasing. So I'm going to go with non-decreasing. So let's say our first term is at 0. Oh, sorry, I should do this right. If the sequence is bounded, it can't just exceed past it. So that means instead, the terms have to get smaller and smaller, or the growth has to be smaller and smaller as we proceed forward. And what you can see happening is basically our sequence is approaching what looks like a horizontal asymptote. The terms are getting smaller and smaller. And in this case, the way we've drawn it, not only do we have a bounded monotonic sequence, bounded because it's got upper and lower bounds, and monotonic because it's uniformly increasing in this case. Oh, I spelled it wrong. Monotonic. We not only have that, but we also have a convergent sequence, which is what this theorem's saying. If you can guarantee that you're both bounded and monotonic, the monotonicity guarantees that you're growing and getting bigger and bigger, but the boundedness guarantees that there's a limit to that growth, meaning that you're topping off. And of course, in this particular situation, you can probably see it. If this is the graph of a sub n, this is showing us that the limit as n goes to infinity of a sub n is actually equal to that upper bound n. Again, it didn't have to, it just happened to be there in this case. So this is why. This is just kind of a convenient follow-up. If we have a bounded monotonic sequence, gosh darn it, it's convergent as well. Now, I've said multiple times that this isn't the essential part of the curriculum. It's just kind of nice conceptual intuition, building, and knowledge. But having said that, I do want to show you one time what this looks like. Truth is, you've probably stopped the video by this point. But if you're watching all the way through, sorry it's taken a little longer. I'm getting used to this feeling again. And again, haven't been saying a whole lot lately. So I do want to just show you what this is like in case this is something that you're going to run into in the future, particularly if you do take something like real analysis, possibly even. Where it turns out that all of calculus is basically underneath, sequences are underneath everything. They're everywhere. But beside the point. So having said that, I've got a sequence here. So it says show that a sub n equals 64 times 1/2 to the n is bounded and monotonic and therefore converges. So we've got a couple things to prove here. Let's start with the, let's start with the topic we've known a little longer. Let's start with monotonic, or the monotonicity of this sequence. So if we want something to be monotonic, we need to think about whether it's going to be non-increasing or non-decreasing. So if we're looking at terms of the sequence, we start with 64 times 1/2, which is 32, then 16, then 8, then 4. So it looks to me like we are in fact non-increasing. So in other words, this is decreasing. But again, I'm trying to be as formal as possible. So non-increasing. So what we want to show is that later terms are less than or equal to their predecessors. Having said that, that would be the same thing as 64 times 1/2 to the n plus 1 is less than or equal to 64 times 1/2 to the n. So, having started there, let's see what we can simplify. Well, immediately I notice that the 64's go away. That leaves us with 1/2 to the n plus 1. Well, that's the same thing as 1/2 to the n times 1/2 to the 1, or times 1/2. And that's less than or equal to 1/2 to the n. Oops. Well, now 1/2 to the n is never going to be 0, so we can divide both sides by that as well. And what we end up with is 1/2. 1/2 is less than or equal to 1. That is indeed true. So what we've just shown is that a sub n is monotonic. And in fact, this is a sequence that we could possibly say is monotonically decreasing, meaning that it's decreasing the entire time, kind of the same way as doing like a strictly decreasing kind of thing. Can it fit? Oh, it doesn't quite fit. Close enough. You saw the work over on the side. Okay, so there it is. We just showed that the sequence was monotonic. Good job, us. Our next move that we want to hit is boundedness. And I will say that boundedness is one of those ones that feels a little bit uncomfortable when you're doing it, at least at the very beginning, especially because we're not looking for the greatest lower bound or the least upper bound. But at the same time, we can do that. So we're looking at this sequence. So that sequence we just mentioned is 32, 16, 8, 4, ... So what we want to find is we want to find first a lower bound. Well, if we're looking for a lower bound, we want a number that's always going to be smaller than all of these terms. Well, something I noticed is that since we're only plugging, well, no matter what we're doing, we're multiplying 64 times positive powers of 1/2. Positive times positive is always positive. So in fact, I could talk about the lower bound as being 0. And the reason is all of those terms are positive, meaning that they're greater than 0. So I'm going to choose my lower bound to be 0. Likewise, if I want to look at the upper bound, or talk about an upper bound, we need a number that's going to be larger than all of those. Well, looking at the pattern of growth, or lack thereof, of this sequence, see that we're starting at 32, then 16, then 8, then 4. So an upper bound just needs to be something that's larger than that first term. So naturally, if you wanted to choose the least upper bound, you could choose 32. But you know what? I know who I am. I'm not going to choose 32. I'm going to choose 42. Because, hey, it's 42. So in this case, what we just have is we've now established some pieces. We can say at this point that all the terms of the sequence, in fact, we could literally say the sequence, 64 times 1/2 to the n, is less than or is greater than or equal to 0 and less than or equal to 42. And again, I'll just establish for all n greater than or equal to 1, since that is pretty standard, but again, it wasn't established in the problem, so I'll say it. So what we can then say is that therefore a sub n is bounded. As far as conclusions go, that was huge, because now we've shown that a sub n is monotonic and a sub n is bounded. And what that means is therefore, since a sub n, and I'll even write out the expression here, a sub n equals 64 times 1/2 to the n minus 1, just n, is monotonic and bounded. I'll write it here. A sub n converges. And by the way, if you were curious, we did not establish what the a sub n it is, what it converges to. But having said that, it seems pretty clear that as you plug in larger and larger values of n, you get smaller and smaller terms. So it's fairly safe to say that this sequence converges to 0. But that's not necessarily something we need to worry about yet today, though in a few lessons we might. So having said that, this last chunk is far less essential than the first 35 to 40 minutes of this lecture. But at the same time, I hope that this has given you a good introduction to sequence convergence. I'm going to post the problem set as soon as I upload this video and share it with everyone. So I'll encourage you to take a look and kind of use that to kind of help yourself and to kind of learn some stuff if that's something you're looking for. And hopefully you are, just because got a lot of downtime, and any work that we do now is probably a good investment for the future and time that you don't have to spend working on it later on. And who knows what's going to happen anyway. So having said that, if you're watching, thank you for watching. Hopefully you're staying safe. Hopefully you're staying comfortable and finding some fun things to do in addition to maybe doing some calculus. Your call completely. And again, thank you. And obviously I miss you. I would much rather be around you than standing here talking to myself, keeping my heater turned off, and talking to a computer screen again. So in any event, thank you for watching, and whether you're watching in the morning, afternoon, or evening. Wait, what is it? What is the Truman Show guy says? Good morning, and in case I don't see you, good afternoon, good evening, and good night. Something like that. I don't know. I got to find a better sign off. That wasn't bad. Okay, thanks. Bye.